Yeah, thank you, promised.
Okay, sir, let's go ahead. We'll start.
Yes,
Yeah, people
yes,
will
yes.
join meanwhile.
Yeah.
Yeah. A
We'll
very
wait.
good evening to all the participants. Welcome back. Welcome to the final session of this ATAL FDP. Um, we have with us Dr. A. Sheik Abdullah. I will give you some brief introduction about Dr. Sheik Abdullah. He's working as a associate professor in School of Computer Science in VIT Chennai. He completed his PhD from Anna University and he's a visiting faculty at the Institute of Mathematical Sciences, Chennai, and contributed and worked in computational biology, mathematical decision support models in clinical informatics, data analytics, and statistics. More recently, he has contributed his novelty in assessing risk factors that contribute to type 2 diabetes with the SWAM intelligence and ML approaches. His work corresponds to real-time analysis of medical data and medical experts with the development of clinical decision support models for hospitals in rural areas. He also contributed his research intelligence in NLP, big data, knowledge-based systems, e-governance. There are many more for his contribution. He has published over 45 plus archival research papers to his credit, 15 book chapters, and a book. Being a gold medalist in PG, he has been awarded the Honorable Chief Minister Award for the best project in governance. He contributes his interest in various international conferences and serves as a reviewer in IEEE Access, Elsevier, Springer, and CRC publishers. He is an active member of ACM and IEEE since July 2015 and also being recognized for his extraordinary contribution to ACM chapter events with ACM faculty sponsored recognition between 2015 to 25. It's a very rich academic background. With this brief introduction, I take great pleasure in inviting Dr. Sheikh Abdullah for this session. Sir, the session is yours.
Yeah, thank you so much. Am I audible, sir?
Yes, please go ahead, sir.
Yes,
You're
yes.
eligible.
Yeah. And I hope the slides are moving.
Yes, sir.
And
Yes, yes.
so a very good evening to the participants. So here myself, Sheikh Abdullah. So I have been assigned with the topic for the ATAL session, the session 13, on AI-based healthcare decision support model for coronary heart disease. I hope that you participants have been explored with plenty of words stating that machine learning, AI, supervised learning, unsupervised learning, and so on. So many logics behind how the applicability of machine learning is devised to different sets of application. Similarly, so in this session, we are about to focus on two different disease prediction models. I want my participants to be eagerly engaged. So not to give a high much of dosage. So this and that, everything is there. No. So at the end of the session, you must have a complete idea about how AI enabled models are suitable for clinical predictions. So that should be the final outcome of this session. So I hope you will be having a complete way of understanding how AI ML is helpful in devising clinical prediction models. So before focusing on the specific term on coronary heart disease, so as everyone knows how the disease CHD is spreading wide vast in recent days. So before going for that, you must have an introduction with respect to biomedical informatics. The term biomedical informatics has been evolved with respect to the intersection of computer science and technology towards healthcare and health studies. So for the past 30 years, we have been identifying and we have been devising new sorts of technological incorporations when compared to the past 30 years. Automated AI-enabled devices are doing surgical operations, right? So to explore the complexity of the disease and to identify how the risk factors that enables the people to have the different sort of symptoms for a particular disease. So that's, we call it as disease-specific syndromes. So in biomedical informatics, we can split bioinformatics, imaging informatics, and clinical and health informatics. So the first category focus with molecular and cell biology. And the second category focus with imaging sciences, that is organ structure and tissue studies in the human body. And the third category focus with the population and health-based study, that is societal study. So the third category focus with disease studies, that is the two category of diseases, as everyone knows. One is communicable diseases and the another category is non-communicable diseases. Okay, so the clinical and health informatics completely focus on population and patient-based health studies. So that's what we are going to explore in this presentation. So these are the three methods as we see in the diagram. Medical aspects, when coming to the medical aspects of communicable and non-communicable disease, as per the report given by the World Health Organization, because for every fraction of minute and every fraction of second, the World Health Organization is preparing their report with respect to the disease-specific syndrome, in which the major problem in India is 62% of encompassment is to total death that is occurred due to non-communicable diseases. And also the expenses when compared to communicable and non-communicable, the hospitalization expenses incurring 160% and higher than for NCD. So that should be taken into an account. The increase in NCD is due to the clinical intervention, dietary habits, and locality of the people. That's what we have to say. So different locations of people will have different dietary habits, that we know, right? Different way of living, different way of having their doing their activities. So everything varies, but we doesn't know how to predict why it happened. Many factors may lead to that particular disease-specific syndrome. So the health awareness, the facilitating factors, the medical complications, everything need to be identified or determined in advance so that the effectiveness as well as the treatment for the disease can be ascertained and identified more easily. So the NCD death for males and females when compared is males are having higher ratio when compared to female. So the death rate for all NCDs, that is chronic respiratory cardiovascular disease, that is about 386.3, which is much more higher than all the other sorts of non-communicable disease when compared to the communicable disease. And before going for a studying or before exploring any sort of disease, we must understand what is the term epidemiology. So epidemiology deals with how the disease is distributed, what are the factors that contribute towards the disease, and how the health affected regions are identified, and specific work group of people or the population. We can understand people working in a particular company are affected with specific disease. People working on a particular zone are affected with particular disease. So what is the reason? We have to identify. The environment is one of the factor that tends to the disease specific syndromes. So these four factors must be kept in advance before going or before studying the disease or epidemiological assumptions. So how the frequency of the disease is distributed, how the distribution of the disease is identified, and what are the social, behavioral, physical, and biological factors. So I will show you the data set. I will show you the entire data set, which has different sorts of risk factors or different sort of attributes that makes the values pertaining to the disease specific syndrome. And in order to quantify all this epidemiological study and epidemiological assumption, we must formulate an AI decision support model which makes or which prevents or which identifies the risk factors that is associated with the disease. So all AI models are not providing a complete way of analysis towards the disease specific syndrome, but AI models provides a pathway to identify the major sort of risk factors that is associated with the disease. So that helps the medical practitioners to identify how a particular value is increased or decreased with respect to the graphical assumptions that pertains to the disease specific syndrome. So while developing an AI model, healthcare data analytics also provides a way of understanding the pattern, because identifying a pattern or exploring a pattern on a medical data provides the significance among the risk factors that helps in identifying the disease at proper stages. So here, the overview provides how an AI decision support model is developed with respect to knowledge discovery from data, and how the clinical decision support system helps in identifying the model, and how the data interpretation and evaluation provides for analyzing the data from different sorts of data source. Because when handling with medical data, we get in different data. One is handwritten data, another one is categorical data, another is continuous data, image data. So everything will be getting. So all these data sources should be unified first into an understandable format. And then only we have to get focused on the development of clinical prediction AI models. All the clinical prediction models provides a predictive way of handling the risk associated with the disease. So that is the only outcome of the clinical prediction AI models. So which sorts of risk factor is responsible for identifying the particular disease? So for this clinical prediction AI model, we'll be using different sorts of data classification AI algorithms that we know already, right? So there are two categories of algorithms. What are the two categories? Can anyone? There are two categories of learning in machine learning, there are two categories. The major two categories. There are more than two categories are there. So the major two categories: supervised learning scheme
And
yeah, unsupervised learning scheme. So if your data has a label value, a data label, then you'll be obviously going for supervised learning using decision trees, random forest, SVM, the boosting algorithm, neural network, and so on. If your data set doesn't have any label, you will be directly going for first unsupervised learning scheme, which involves algorithms for clustering the data set. That is for k-means, k-middoids, hierarchical clustering, and so on. Right? So, based upon the data, because not all the medical data, whatever you are getting in hand, will have the label that you know. Even getting a medical data is one of the tedious tasks in real-time mechanism that everyone knows. No one will give the medical data that can be handled should be handled very seriously. So there are cost-sensitive methods which makes the clinical prediction, which aims in determining the misclassification cost and test cost. Because why I'm saying this? So before going for a medical test, previously, what is the prediction that is made by the AI model, which stops you to make or to enter into the next stage of analysis, which cuts your cost and test unnecessarily. So that can also be done by the clinical prediction models. And also, there is a part called computational cost and other algorithms which needs to be addressed for the data set. The next is swarm intelligence in clinical AI data prediction. As we know, this is one of the category of AI-driven models which corresponds to the classification of algorithms on natural learning behavior. So these algorithms will synchronize themselves using self-organizing and self-distributed control mechanism that makes themselves to have an environment that can be developed, which enables excuse me, please, could you mute yourself? Thank you. So these algorithms provides a distributed control mechanism. They develop their own environment. They integrate with data classification schemes, and they provide a decision support model that can be used for identifying or predicting the risk that is associated with the disease. So here we are going to see two different types of models. One is the swarm intelligence based and colony based data classification model for coronary heart disease, and particle swarm optimization enabled data classification based decision support model for type 2 diabetes. So these two models that we're going to see now, and I will show you how the data set is used for developing these two models and what is the code that is generated against these two models and what are the results that we have got as an outcome of these models in action. So the swarm intelligence in AI prediction provides certain properties such as the group of individuals, homogeneity learning, heterogeneity learning. So here there are two different aspects. One is learning among themselves and learning from the environment. So these are the two factors that is fixed with the swarm intelligence techniques associated with the data classification scheme for AI prediction. Professor, please could you mute yourself?
I'm trying to put him. Can you mute yourself?
Elegant, sir.
It's okay now? Is it okay now?
Yes, sir. Thank you so much.
Yeah.
So, before I said swarm intelligence plays a role in, so it is a part of AI in prediction, and without statistical schemes or statistical approaches, we can't provide a valid AI-driven model in healthcare analytics. Because all statistical measures provides an evidence-based learning. So evidence-based in the sense understanding the patterns behind the data. So what is the pattern that is identified from the given model? Okay, so analyzing the features using swarm intelligence models, applying those features, that is correlated features, to data classification schemes, that is supervised learning schemes, and then visualizing the evidence through different forms of statistical approaches in medical data, which provides the complete pattern behind the analysis, in which how machine learning provide a high demand in exploring the discipline with respect to better clinical prediction and research interferences. So here the target is identifiable with respect to different forms of statistical schemes such as linear discriminant analysis, correlation analysis, chi-square models, and developing certain ROC patterns. Okay. So the main motivation behind the selection of these type of AI-driven model is only due to the technological innovations and the technological incorporations from medical point of view, because nowadays we are identifying and visualizing different forms of AI-driven automated equipments which serves or which aids as the factor for resolving certain forms of disease. So they work with respect to the AI-driven model that is inbuilt on the device. So those AI-driven models will have a scheme or classification model or algorithmic model that disseminate the risk factors that is associated with the particular disease. So here, determining the disease-specific risk factor and identifying the inconsistencies in the data or decision support model is the key motto to identify the research. And current research challenges in coronary heart disease prediction is the scalability of the machine learning algorithms, new computational models, data acquisition, data complexity, real-life case studies, and risk factors related to non-communicable disease. So these are the most likely impact that is identified for the AI-enabled scheme. So here, AI-enabled data models for CHT prediction. Here, this presentation explores first a novel clinical optimization unit that can handle any type of medical data and provide a consistent result with respect to the risk factor prediction. And then, ant colony-based decision tree model, which is used for determining the risk related to coronary heart disease, and particle swarm based decision tree model, which is incorporated with respect to a self-adaptive inertial weight with modified convergence logic. So that is the novel part that is used with respect to the AI-driven model. So in that second part, PSO model, it is validated and tested using Fisher's linear discriminant analysis for determining the risk factors related to coronary heart disease. So this is the complete focus of the presentation. So first, let me show you. So this is the mortality rate from NCD. So it is getting increased for cardiovascular disease and death by cause in India. The death rate is increasing. So you can see the blue color, the dark blue, which is for CHT, the ratio of CHT when compared to other disease. So first, let me show you the intelligent optimization unit. Yeah. So with diverse disciplines in medical field in making the data processing, because identifying the data is not a matter. So we have to process the data, make the data readily available. We have to identify the features or the attributes associated with the data. We have to apply the suitable AI or ML model, and we have to predict what is the outcome or what is the final thing that is identified as a richness of domain and the pattern that is identified from the data. So here, when identifying the clinical prediction models and supervised learning models, so they generally fall into three categories. One is statistical model, sophisticated model, and survival model. Okay. So here, we are going to identify the fixation of operating parameters and learning factors for the algorithm developed. Directly applying an algorithm, getting a result is not a matter. Everyone can do, right? How I am fixing the operating parameters of the algorithm. How I am fixing the learning factors of the algorithm. So that should be a dependent outcome with respect to the variable or the features that I'm using for my research. So here we are using a intelligent optimization unit. So this unit is a generalized unit, and a statistical evaluation can also be made at multi-stage process for processing the data with this unit. And here with the labeled data, we can process different forms of standard data standardization techniques before going for analysis with the intelligent optimization unit. And then we can provide the features associated with the data, and we can process for developing the algorithmic model for using the swarm intelligent techniques. So this is the generalized intelligent optimization unit, which serves as a guideline for making the model to be stipulated in a real-time operating environment. Because you need to understand there are two different ways or two different platforms in which you can use the data set to be processed with respect to different arena. One is real-time data and another one is batch data. So batch data, which is readily available in any of the website that you can collect from Kaggle, or the data that is available in repository, that is stored locations, right? So that data you can take process. So somebody has deposited the data. You can take those data from UCA repository is also there. Kaggle is also there. You can take those data. So you can process. You can identify a model, provide a valid outcome. That's all, right? My model is the best. And the second category, real-time data. What is real-time data? I'm getting or collecting a data in real time from a hospital which has a different set of attributes, which makes the environment to give some real input at different stages. Real input is given, and that input serves as a valid outcome for providing certain clinical decisions. So here, once the data is collected, first I have to identify the general information related to the disease. Second, I have to identify the comorbidities associated with the disease and information related to imaging sciences. And finally, the investigation reports that collected from the medical expert. So all this needs to be categorized. And then only I have to go for processing my data with respect to training or testing, whatever that thing may be. So here I have to identify the initialization part, and I have to get ready for training and test, and I have to check my data is valid labeled. If not, I have to go for dirt chart advisor. So the advisor provides how the value can be labeled, and then it has to be sit under a discussion forum. And finally, clinical experts or trials should be given with respect to the unlabeled part. Then if it is labeled, I can directly go for a classifier. I can go for a training rate, and I can go for fitness evaluation. I already told that here we are using the SWAM intelligence techniques for selecting the features. Once the features are selected, and I have to check for the condition with respect to the optimized feature set, and then identify the risk factors. Once the risk factors are identified, then apply the statistical approaches for the pattern or the relationship that is identified for the risk factor associated with the data, and locate or deploy the risk factors and interpret the risk factors with the medical practitioner in order to identify the real-time root cause of the disease that is associated at different stages. So this is how the real-time analysis works. At that point of time, at the point of interval, the disease specific reasons or the risk, what type of risk is associated, will be completely identified and fed as an input to the next level of disease prediction stage for coronary heart disease analysis. So this is a description pertaining to the intelligent optimization unit. So training model, testing model, training model, a data classification component is built, and the testing part, the classification part is evaluated and verified on the test model. So here I can show you some data pertaining. So So this is the real-time coronary heart disease data that is collected from the hospital under ethical committee clearance for doing real-time research work. So here, this data set contains different set of attributes, as you can see, right? Age, sex, chest pain type, cholesterol levels, weight, hypertension. So each category is having a value depicting the occurrence or the non-occurrence of the particular attribute. And finally, it is having a class label. As you know, right? What is a class label? If you know, I can continue. That's what I'm asking, because we have undergone many sessions on AI and ML. You know, right? Class label.
Maybe it is a classification based upon the criteria or parameters.
Yes, sir. Obviously. So here, the class labels are two different categories. One is binary class label and another one is multi-level class label. So for binary category, there will be here, there will be only two categories, either 0 or 1. Two categories only will be there. So here I am having more than two categories, right? There is 2, 0, and there will be 3 also. 1 is there, isn't it? So more than two categories, and I can say this type of class label as multi-level class label. I will show you the description of the data set. So this data set is having, yeah, this is the description. So each attribute, age we know. So here I have categorized age into how many categories? 1, 2, 3, 4, 5, 6 categories. And the second attribute, sex, I can categorize as two categories. One is male and female, 1 and 0. And the next is third attribute, chest pain type. So here see how many chest pain type I'm having. Till IKL, compressive type, restational type, pricking type, substrational type, chest pain with jaw and neck pain, pain at rest, no chest pain. So for these different categories, here I will have mentioned as these different values. So totally I'm having 12 different categories. That's what I have mentioned, different values here. Are able to understand the data set first? Yeah. So first, the data set should be clear for processing. Unless otherwise, we can't make certain predictions with respect to the input data. So here, this is the different of attribute description. So systolic blood pressure, normal level, abnormal level, diastolic blood pressure, normal level, abnormal level, cholesterol level. So here I have 3 different levels for cholesterol, level 1, level 2, and level 3. ECG results, smoking. If it is smoking, no, 0, smoking, yes, 1. So like this, I have categorized, or I have made my data set to be more clear for next level of data processing, which makes the prediction to be more easier and compatible for analysis. One thing you have to keep in mind. So here I have multi-class class label. So let me see how many different categories of disease I mentioned here. Yeah. So here for class 0 means it is angina, the first level of disease, heart disease. Class 1, myocardial infarction. Class 2, percutaneous coronary intervention. Class 3, coronary artery bypass graft surgery, which is the final level, that is bypass will be done. So that comes under the category of class 3. So this data set has been accumulated from a government hospital in which they have provided under an ethical clearance committee for complete research work. So with this data set, we are going to see how the predictive AI model is about to be developed, optimization along with decision trees for coronary heart disease prediction. So data set that is accumulated. So in addition to this coronary heart disease data set, we have also collected a type 2 diabetic data set also. So the type 2 diabetic data set, we have processed using swarm intelligence model, that is particle swarm model, along with the data classification, different sorts of data classification schemes. And we have developed the AI-enabled platform for that decision support model. And we have deployed the same in that particular hospital. And we have checked the ratio of that AI-enabled decision support system, which worked for the rural people. Rural people we have identified and predicted the certain sort of region-based risk factors for that particular coronary heart disease. So here, this ant colony model is a meta-heuristic method for finding the best path in a weighted graph or a weighted input. So this biological scientists have proved this process of movement of this ACO model, that is a movement of ant, which deposits a certain quantity of value called a pheromone. From that, this algorithm work, which is accelerated through the pheromone value of the edges in the graph. So that is the thing which makes this ACO model for working towards the exploitation of the behavior of ants. So there are different parametric values that needs to be ascertained for ACO model. So here the features are identified, that is the attributes are fed as an input to the model with the ACO algorithm, and then the decision trees are used for classification purpose. So why we have selected decision trees? Because it provided good significant results when compared to other data AI classification schemes. And then we have generated the fitness value, and we have identified how the determination of best combination of risk factors is identified for classification scheme. So first, this ACO provides a pheromone initialization part. So moreover, it provides a softmax activation scaling function, which is used to fix the normalization values within the scale of 0 to 1. And then the matrix is generated based upon the number of features. So the matrix provides the entire set of values, that is to generate the population in which how the number of features are fed as an input to the model. And then we fixation of parameters is identified with respect to the number of features that is generated or aligned with the initial population. And the similarity matrix is used for determining the probabilistic level using the equation that selects the next features according to the Fi and Fj value. So argument of max value of that Fi and Fj, that is the first feature and the next feature with respect to the alpha and the beta parameters according to the following equation. And the best feature is identified using state transition rule. Once the best features are identified, then the next pheromones are updated using the pheromone update rule using the formulated equation. So pheromone updated, here we will be taking all the summation of the features with respect to the I and the J component. And then the acceleration is made with respect to the t+1 value and the t, because the previous time and the next level of movement has to be identified with respect to the feature updation as well as the velocity updation rule. So that's why if there is a set of similarity exists, then the features are noted and it may lead to pure accuracy. That's why once the features are identified, it should be noted whether it is same or the different features during the traversal of the graph. Then the feature with high value is identified, then it should be updated using the new information using the following equation. And this is the flow with respect to how the evaluation of this particular model is used. So here, the first thing, once the fitness is evaluated, we have to initialize the counter. We have to initialize the counter value to 0, and we have to determine the shortest length, and the best solution is initially identified to. Then only the flow has to initiate with the initialization of ants, movement of ants through the next state, and movement of ants to reach the final state. And then we check for the deposit of pheromones and the demone values. And once it is done, we simulate the evaporation of the strengthening of the pheromone value and update the value with respect to the criterion that is reached. Once that is reached, we have to check with the final decision making with the model that is developed for determining the best features using the fitness function. So here I have used two different conditions. Once the stopping criterion is met, I can stop the value, or once the number of iterations is reached, then I can stop the value or the condition to terminate it. So this is the algorithm that what I have told as of now. So set of input, what is the input that we are giving and what is the output that we are getting. The inputs are the number of training features, the total number of iterations, the number of ants in the entire matrix, that is a similarity matrix, and the number of features to be given as an input. As an output, you'll be getting the selected features at the final stage for execution. So this is the workflow of the algorithm. And once this procedure for ACO is complete with the set of selecting the features, then the procedure for the decision tree starts. So here with this tree, we'll be giving the input as number of training observation, number of candidate attributes, and the splitting criterion will be giving. So here for decision trees, there are three different splitting criterion. One is the information gain ratio, and Gini index. So whatever the criterion you wish, we can give, but different values will be ascertained for different splitting criterion. We have to check and we have to identify which splitting criterion works best for this particular data set, and then we have to proceed for executing the results. So lastly, so we have modified once the execution is stopped. So for I is equal to 1 to the number of training tuples, we have made two different things here. If class is predicted class of testing data, then I have to check for positive tuples. If positive tuples at the stage, I am incrementing positive by 1. Otherwise, if negative tuples means I'm incrementing negative by 1. So why I am doing this? Because for fitness evaluation, I can make things to be executed or make things to be clear with respect to true positives and true negatives with respect to the total number of cases. So these are the metrics that are used for evaluating. We can use any metric, but the thing is which metric provides or suitable for the data set that we are using, that should be identified. So this is the results that we have got with respect to heart disease prediction, 92.51 when compared to other. And type 2 diabetes also we have got the highest accuracy. And this is the analysis of time complexity. So for this model, we have measured the time complexity F as number of features and number of patterns that is generated for the general matrix big O of F of n. And the total time complexity is big O of F square of n for the ants to explore the search space, because there needs a time to explore the search space and to identify the different perspective of the learning model. Hence, the time complexity measure is provided here. And more probably, ACO decision trees provides a good value of identifying the fitness with respect to the provided value. So here we'll be using the evaluation mechanism of Java execution of this file. So and then we have practiced the same with respect to Python Google Colab that executed more strengthened than the Java executed file that we have provided here. And this provided with respect to the real-time data as well as the benchmark data. It has provided good results with respect to the accuracy value of 94% for cancer also, and for real-world data set maximum accuracy for accuracy observed was 94% for type 2 diabetes. And this provides improvised way of analyzing the predictive way of handling the data with the ability to determine the minimum number of relevant features and improved accuracy. So this is why this is what the predictive AI model that we have determined and deployed the same at a hospital, government hospital, for identifying the risk factors that is associated with the coronary heart disease. And this is the second model for identifying the risk factors that is associated with type 2 diabetes. So here in this model, we have used, we have first cross-verified the different methods, that is enumeration methods, gradient methods, random search methods, and meta-heuristic methods. So we have made a complete limitation and usage and analysis, and we have identified a proportional mathematical calibration to check which method has its own identifiable search space with respect to the environment, because the environment plays a major role in identifying the search space for exploring the number of features that is used for evaluating the model. So that's what. And here, with respect to prediction for this type 2 diabetic data, we have identified an improvisation for PSO algorithm with respect to specificity, comprehensive nature, transparency, flexibility, and data validation. So with these specific characteristics, decision tree provides a framework to quantify the observed values to make a decision. And here, with respect to particle swarm algorithm, so it works with respect to the flocking of birds, and it works with respect to the two different values, the P best and the G best, that is its own best and the best that is observed from the environment. So the particle best, as we see, the number of best students, the best student in a class, and G best, that is the global best, that best students in a campus. So like these two values plays a major role in determining which features is the best feature, which feature plays a major role in determining the role for identifying the risk factors that is associated with the disease. So here, this algorithm works with the current position, the current velocity, the distance between the current position and the P best value, that is it's my own best, and the distance between the current position and the G best value, that is the global best.
Hello?
Am I audible?
Yeah, just now, I think there was a disconnection. Now it is audible.
I think it's weekend started and we are having very slow bandwidth, I think.
What's that?
For the last 5 days, we have not had any bandwidth issues. Now, as
Okay.
the weekend started Saturday, there is little bit of network connectivity is becoming
Okay,
issue.
okay,
Yeah,
okay.
yeah.
I think now it's right? Perfect, right?
Now it's right. Yeah.
Now it is right,
Yeah.
sir. It's perfect.
So this is the search space in which the given environment for the determination of the best value, that is the P best and the global best value, to determine the velocity and the position of the feature for the given search point. Okay. So the size first we have to give the input, that is the predefined input, that is the number of features x1 to xn, and then we have to identify the first new position that we have to check and give, and we have to give the first new position for each set of feature, and then we have to identify the objective function for each set of feature. So here I'm giving the initial population, I'm providing a position for each one, and I'm providing the objective function initially for each one. And then first I'm identifying the position, that is my position, what is my current position and what is my current movement, that is identified by PI of KS1. So here there are two different factors that plays a vital role in determining this movement of each and every feature that is associated with the algorithm, that is C1 and C2, that is cognitive and social learning factor. So the author who have identified this algorithm, they have experimented different values for C1 and C2. So let me show you in the forthcoming slide. And here, how the convergence takes place. So the determination of convergence of the algorithm is taken place by the following condition. So as we know, first thing, the maximum number of iteration is reached. Once the solution is accepted, I can stop. And if there is no improvement, we have to keep it in mind. If there is no improvement, because no algorithm will give good results at all the data sets, right? So if there is no improvement over the generation of swarms, and if the radius of the swarm is closer to 0, the condition gets terminated. And if the slope of the objective function is also close to 0, then the condition gets terminated. So here, for this P best and G best position, the velocity of the ranges identified to high value, the set of selected feature is fed as an input to the J48, that is Java implementation of C4.5 decision tree AI algorithm. So here, the algorithm proceeds with the input parameters, as you already know, the training data, what is the input data set, the list of attribute, and the splitting criterion, which splits the determined identified value. So here we are using the information gain to use the splitting criterion for the values. Okay. So here I'm using information gain PI log base 2 of PI. So that is the value I'm doing. And here for this recursive partitioning, I'm identifying if the tuples all belongs to the same class, I'm stopping the thing. If there is no attribute for further partition, I'm stopping the thing. And if there is no tuples for identifying the branch, I'm stopping the case. So these are the conditions for this C4.5 Java implementation of decision tree algorithm. So I have given the input parameters. I have fixed the conditions for the swarm algorithm. I have fixed the condition for the data classification algorithm. Now I'm going to execute the things. Right. So here the fitness is evaluated using the following condition. If the current fitness is lesser than the local best fitness value, or the current fitness is lesser than the global best fitness value. So these are the two conditions I'm going to use for evaluating the fitness value of the function. So this is the workflow. Here, after evaluating the fitness, I'm checking the position for each particle. Current fitness is and the local fitness is equal to current position. Okay, So here, and at each iteration, I'm checking myself whether I'm getting the highest mark or the highest value and compared to others. And also I'm checking whether I'm the highest among all the students in the class. So everything, all the students in the class. Also, I'm checking myself whether I'm the highest among all the students in the campus. Right? So these are the two factors that needs to be checked all the times during each iteration. So this is how the best feature is selected at each stages. So here we have used a total of 732 subjects, 732 cases were collected. Okay, under the examination of a medical expert, and written permission and study was obtained from medical expert for the medical study. And recently, we have also got a data set from 2016. It's a 5-year data set. So it is also 16 to 2021. And we have analyzed those data set also in a case study with respect to the subjects of type 2 diabetes. And we have compared these two data set, that is before 2016 and after 2016. And we have formulated a set of risk factors with respect to the three major problems associated with the disease. One is the location of the people. The second thing is the dietary habits of the people. And the third thing is the people, how they make things to happen, how they engage themselves in different activities. What are the work process they are doing? So based on that, also we have identified the things, and we have got very good results with respect to from the medical practitioner point of view, and we have analyzed the examining reports of different perspective, and we have fixed the cases that this is the risk factors that is pertaining to that particular group of people in the particular location. And this is the modification we have made to the scheme or the algorithmic model for evaluating the significance of the process. So here, all the values are set to 0. If the value is less than n, I'm identifying and making a check for predicting the classes. Yes. If class is equal to predicted class, then I'm incrementing the true positive value. Otherwise, I'm incrementing the true negative value. Finally, I'm evaluating the fitness. So different sorts of normalization scheme is used. So here we have used Z score normalization. Z score x minus mu by sigma. And processed data, we have 24 attributes. So here I have to highlight that's two different learning factors, C1 and C2, cognition and social learning factor. So there's a formula for this. So here we have used different values. First, we have checked with C1 equal to C2 equal to 0. And that happens, no cognition learning and no social learning took place for the execution. And we have checked C2 alone 0. There occurs no social learning among the particles. And we have checked C1 alone to 0. And we have checked there occurs no cognition learning. And there, unless the information is shared among the particles, each one of the particles is said to run independently. Okay, so the next thing, so after C1 and C2, the next highlighted thing that needs to be considered for evaluating the model is the inertial weight. So here we have proposed a self-adaptive inertial weight with modified convergence logic. So that is the thing we have proposed here. So as per Kennedy and Eberhard, they have fixed the value C1 and C2 are set to C2 as recommended for same effect in velocity and the position update for making the particle to be more clear. So here, this is the incorporation, or this is the novelty we have included in this model, AI model, with respect to modified self-adaptive inertial weight with convergence logic. So this is the equation we have deployed for making the particle, that is for making the feature to move from one place to another place. So Vi of n plus 1 is equal to W into V. The W into V, that is the current velocity plus F, that is the feature. Okay. So here, with accordance to this, we have made the modification with respect to the particle swarm algorithm, and we have executed the fitness with respect to the execution of the model, and we have calibrated the new fitness value. So the acceleration of the weight factor, we have checked the weight factor value with respect to the inertial weight values starting from 0.4 to 1.3. That is, the inertial weight value is calibrated using the self-adaptive inertial weight with modified convergence logic. For different values of weight, we have checked, and for 0.9 ratio scale, it has been given an output of about 98.60 accuracy with the determination of the each and every iteration. So here, this is the particle number and the accuracy value for the execution of number of iterations that is ascertained with the different values of measurement of performance metrics. And here, for the value, when it is fixed between 0.8 and 1.2, the algorithm provide a better way of search space to identify the exploration with respect to the learning factor. So these are the metrics used for evaluation: weighted mean recall, F score, absolute error, RMS error. So as an output, we have identified the risk factors as postprandial plasma glucose, isolated hemoglobin, mean blood glucose level, fasting plasma glucose. So these are the attributes that are identified as the most predominant attribute for the patient with the high values of resemblance that needs to be monitored seriously for the different cases that is considered for evaluation as an outcome of the AI model. And finally, we have used the association of the risk factors and the correlation between the attributes using Carl-Pearson coefficient. So with this coefficient value, we have identified, because if one value affects the resemblance of the another value, then it is made more easily for the value determination. So this is the tree level that is generated by each and every level of analysis with respect to the lower value and the higher value. Postprandial plasma glucose, which is the root node that is identified for among all the other nodes for resembling the value in which how we can get the level of significance from the two different categories of analysis. So it is followed by fasting plasma glucose and glycolated hemoglobin. So this is the correlation value that we have obtained for the determined risk factors. And we have also found that cross matching of the risk factors that is obtained for each and every level for a combination, and R square values also computed to be more good when compared to the other such results. And we have compared the number of features selected for our model when compared to the other such model or the proposed by the other such authors. So that also resembled good with respect to the incorporation of the accuracy that is obtained from different authors. So that also compared, not only we have compared the accuracy, we have compared every factor. So starting from the association among the risk factors, the formulation of the risk factors, and the risk values that is retained. And here we have checked for hypothesis also, because that also plays a major role in determining the observed values versus critical values. So here we have used Fisher's F asymptotic approximation to determine the F value, F critical value, that also resembled less than 0.0001, and the test evaluation and ROC provides a threshold of about a good percentage of sensitivity and specificity for both the cases, that is positive cases as well as the negative cases. And this is the value that is retained for getting the sensitive cases. And this is, let me show you this code. So this is the code that is used for executing the model. So here we have set the initial velocity of the particle, and then we have entered the accuracy for getting the fitness value. And then here, this is the p best for updating the, if the p best is updated, it will be updated in the array. If the p best is not updated, it will be dissimilar, not updated. And finally, the resultant of g best is also calibrated here. And the updated g best is checked with the previous value and the next value. And the value is stored in GB2, that is the highest value of G best. And then the velocity is calculated at each stage, and the new velocity is calculated using this equation. Vi of j is equal to weight into, weight is the weight value that is will be giving from 0.4 to 1.3, and the current velocity of I comma j. C1 is the cognition landing factor, random is the random value, and in PB is the current best, that is my best value, that is the next P of ij, that is the current position, and then plus C2. C2 is the cognition social learning factor. In the random 2 is the second random value that is generated. GB2 is the GB2 global G best value, and PA of J is the position of the particle. So this is the equation. This is the important equation that is used to calibrate the thing at different stages of evaluation. And finally, based upon the value of Vij, the new velocity of the particle will get generated. And once a new velocity is generated, then I can generate the new position, because I know Vi of j. Vi of j is the new velocity. Pi of j is the current position, and this Pi of j is the new position. So from this, I can calculate the new position. Once the new velocity and the new position are calculated, I can check for the G best and the P best value, and I can store it in my updated particle matrix. Okay. So once it is updated in the particle matrix, I can check with either with accuracy or with the number of iterations. So here I can check with accuracy also. I can give 98. Unless the iteration reach 98% of accuracy, my algorithm will run. Okay. Or else I can fix up with the number of iterations also. So this is how the algorithm works, and features are calibrated. And this is the ROC curve that is obtained as a part of execution. So here, with respect to the development of decision support and AI model, we have incorporated real-time data for CHT prediction. The model that we have used is swarm intelligence-based data classification, AI-enabled model. And we have identified different sorts of risk factors pertaining to coronary heart disease prediction. And we have made things clear with respect to this is the diabetic data. So this is the diabetic data. Age, fasting plasma glucose, postprandial plasma, glycolytic hemoglobin, mean blood glucose, total cholesterol, triglyceride level, lipoprotein, high density lipoprotein, non-high density lipoprotein, blood urea. So this is the complete data set that is collected for type 2 diabetes. So type 2 diabetes data set is also it is of category binary class label because it has only two different categories, either 0 or 1, having the disease and not having the disease. Okay. But for heart disease data set, we have identified 4 different categories. One is for angina, myocardial infarction, percutaneous coronary intervention, and coronary artery bypass graft surgery. So like this, we have collected different real-time data sets from different hospitals, and we have made things or developed models for we are in the stage of developing models for different hospitals also. And based on their request, we are providing certain AI-driven automated models. And as you can practice with the different sort of open source tools for learning the model with the different tools that is plentifully available, that you can do it out for learning, for simple learning of AI models for or the predictive models. You can learn using different sorts of open source publicly available tool for easy learning without coding. So doing with coding is one of the best practice that can enable us to have a good sort of understanding that we did how we go step by step and how we execute step by step. So that should be made into practice. So here the significance is made with respect to the improvement with respect to the self-adaptive inertial weight that we have made, because self-adaptive inertial weight with modified convergence logic is the incorporation, because